Morning, everyone. Today we're going to get started on section 9.3, which is a lot about radical expressions and square roots. And we're just getting started here with simplifying radical expressions. And so we're going to see a lot of rules that might seem kind of arbitrary, but when you think about the history of these rules, they all kind of come from the time when you didn't have a calculator and you couldn't find the square root of 5 really easily, let alone the square root of 10 or the square root of 20. So what they did was they created a lot of rules which would allow us to find the square roots of a lot of these numbers just by breaking them down into um, square roots of basically prime numbers. So let's take a look at those, and here we go. This section begins with a lot of, are these equivalent? And these are basically challenging us to try to figure out what the rules of square roots really are. So this first example that we have here is radical 36 plus radical 64 equal to radical 36 plus 64. So let's check it out. What is radical 36? Well, radical 36 is equal to 6. Radical 64 is equal to 8. So when I say radical 36 plus radical 64, that's the same thing as saying 6 plus 8, which is 14. Now on the other side of things, we have the square root of 36 plus 64. So notice here we're going to do the addition first, and then we'll take the square root later. 36 plus 64 is 100, and the square root of 100 is 10. So notice that these are not the same. Not the same. Okay, so is radical a plus b the same thing as radical a plus b? No, not. Okay. And what we're saying is we have a counterexample. Basically, a counterexample is an example that shows the falseness of a hypothesis. So in ours, if we used radical 36 plus radical 64, we found that that is not equal to radical 100, or radical 36 plus 64. So it's our counterexample. Does the same thing work for multiplication, though? Let's try multiplication this time. Since we got started on that talk of counterexamples, a supporting example, maybe it lends strength to the hypothesis, but it doesn't prove the hypothesis. So we're not sure that radical a times radical b is the same thing as radical of a times b. But we have some evidence to suggest that it is true. Okay, let's take a look at subtraction. Radical 64 is 6. Radical 64 is 8. Radical 36 is 6. And 8 minus 6 is 2. How about if we subtract first? What is 64 minus 36? Square root of 64 minus 36 is equivalent to the square root of 28, which I just looked up is 5.29. Notice that in this case, let's circle that in red just to show that they're different, we've got different numbers. So this is an example where the hypothesis was not proven correct. So this is a counterexample. So is the square root of a minus b equal to the square root of a minus b? So no. We have a counterexample. The square root of 64 minus the square root of 36 is not equivalent to the square root of 64 minus 36. Last one here is a division. Square root of 100 is 10. Square root of 4 is 2. So let's do the square roots first. Square root of 100 divided by square root of 4. That's the same thing as 10 divided by 4. That's 2.5. Okay. How about, let's see. Oh, mistake. The square root of 4 is 2, and 10 divided by 2 is 5. Next, let's do the division first and then take the square root after. So 100 divided by 4 is 25, and the square root of 25 is 5. This is good because the two square roots are equal to each other. So is the square root of a over b equivalent to the square root of a over b? Yes, it is. We have supporting evidence. Remember, we didn't prove that it's true. We just have an example that shows that it worked out this one time. See what goodies are in store for us next. Okay, so a counterexample, which is what we've talked about, is an example that proves that a general statement is not true. For each general statement in exploration 1 that is not true, we're going to write our counterexamples, and luckily for you, I remember them. So firstly, the square root of a plus the square root of b is not equal to the square root of a plus b. Our counterexample involved the numbers 36 and 64. And actually, our second hypothesis, which was proven incorrect, square root of a minus the square root of b equals square root of a minus b, that was proven incorrect using the same two numbers, 64 and 36. So next, how can you multiply and divide square roots? Well, you could multiply first, or you can divide first, and then take the square root next. Or you can take the square root first, and then multiply and divide after. Most of the time, people will say that this is easier, since it's easier to find the square root of a smaller number than it is to find the square root of a larger number. For number 5, we have algebraic rules for each operation, and this is basically what they had written in the previous page, which was, of course, the square root of a times the square root of b is equivalent to the square root of a times b. But I think it's really important to know that that fact can be used in reverse. In other words, the square root of a product of a and b is the same thing as the square root of a times the square root of b. In fact, that's how we're going to use it mostly. Same thing with a quotient. The square root of a over b is equal to the square root of a over the square root of b is equivalent to the square root of a over b. But it's more helpful if we know that the square root of a over b is equal to the square root of a over the square root of b. So the order is in which you execute the division or the multiplication in relation to the square root doesn't really matter. We have a few definitions next, and we'll fill them out for you real quick. Here we go, nice and typed out. Counterexample is a specific example that shows that a hypothesis is incorrect. If a hypothesis is true, that means it works for every example, and even one counterexample means that the hypothesis is not correct. A radical expression is any expression that contains a square root or a radical sign. The simplest form is the form where all radicands have no square factors, and we'll talk about that later. Square factor, of course, is if 4 times 4 or 16 is a square factor. Rationalizing, which we'll do later, it's a process of removing a radical from a denominator through multiplication. And the reason why we use rationalization is because it's so much easier to divide by a whole number than it is to divide by a radical. Conjugates are special pairs of radical expressions. So if one radical expression is a plus b root b, the conjugate is a minus root b, and vice versa. The conjugate of a minus root b is a plus root b. And lastly, like radicals are radicals that have the same radicand. So here are some examples of simplifying square roots. And the process is to look for perfect square factors. So this one, we had, for example, the square root of 45. Well, are there any perfect square factors? And you can count them. I highly recommend you just write them and memorize them all. But they are 1, 4, which is 2 times 2, 9, which is 3 times 3, 16, which is 4 times 4, 25, which is 5 times 5, 36, which is 6 times 6, 49, which is 7 times 7, 64, which is 8 times 8, 81, which is 9 times 9, and of course 100 is 10 times 10. Now there are an infinite number of perfect squares, but you just need to know the first 10 of them to have some kind of facility with algebra. If you continue on to higher math, you'll probably want to memorize more and more perfect squares. But right now, you can pretty much get away with just memorizing these. So I take a look at this list of perfect squares and I say, what's the biggest one of these that go into 45? And we can cut out almost half the list because you know the number that divides into 45 has got to be less than 45. So it's none of the last four. 36, no. 25, no. You can grab your calculator and see that 16 doesn't work, which means that 9 is the biggest one that goes into 45. So this is the same thing as the square root of 9 times 45. I'm sorry, 9 times 5, since 9 times 5 is 45. Next, you're going to use the properties of radicals that we just learned to split that up into the square root of 9 times the square root of 5. And then you're going to know that since we're doing a square root of 9, you know the square root of 9 is 3. So this is equivalent to 3 square root 5. We can do another one if you like, square root of 75. So let's see, of the numbers on my perfect square list, which I highly recommend you write down, is there a number, what is the biggest number here that goes into 75? Well, either grab your calculator and divide. 64, no, doesn't divide evenly. 49, no. 36, no. 25, yes. So 75 is the same thing as the square root of 25 times 3. And I'm always putting that perfect square first because that's going to be the part that actually gets broken down through the square root process. So try to put that perfect square first. This is the same thing as the square root of 25 times the square root of 3. We just learned that. And then the square root of 25 is 5. So this is equivalent to 5 square root 3. This is a similar process for square roots of fractions or rational expressions. You take the 3 over 4 and you split it up into the square root of 3 over the square root of 4. And then you say, well, the square root of 4 is the same thing as 2. So this is the same thing as the square root of 3 over 2. Now, are there any radicals in the denominator? Well, in this example, no, there aren't. So you don't have to go through that process of rationalizing that we talked about earlier. I'm sure before we're done, we're going to have to rationalize something. Let's take a look at these extra practice problems, and we'll start with 24. It's always handy to have the list, so I'm going to write the list of perfect squares. And then we'll say, what's the biggest one of these numbers that divides into 24? Okay, so we usually start reading from the bottom of the list, or the biggest numbers. We can start at 16. Does 16 go into 24 cleanly? No. Does 9 go into 24 cleanly? No. Does 4? Yes. So the square root of 24 is the same thing as the square root of 4 times 6. which is the same thing as the square root of 4 times the square root of 6, which is 2 radical 6. There we go. Let's try 36. Sorry, number 3. We've got 162 g to the 6th power. Well, we can split this up into the radical 162 and then the radical g to the 6th. Okay. How about 162? Is there a number from this list that goes into 162? How about 100? No. 81? Yeah, 81. 2 times 81 is 162. So I'll put that perfect square first. And then how about g to the 6th power? Isn't that just the same thing as g to the 3rd power times g to the 3rd power? Yeah, it is. Okay. 81 times 2 is the same thing as the square root of 81 times the square root of 2. And this is the square root of g cubed squared. Basically, you're always dividing that power by 2. Let's see, square root of 81 is 9. So 9 radical 2 g to the 3rd power, and it's always polite to put the radical last in the expression. So this is 9 g cubed square root 2. Okay. Let's take a look at let's go to number 6. Okay. Number 6, we've got the negative square root of 6 over 49. We know that's the same thing as a negative of rad 6 over rad 49. Radical 6 doesn't break down, but radical 49 does. In fact, radical 49 is on my list. So this is negative rad 6 over 7. Okay. Let's see. Let's do 7. Like we said before, you can break up the numerator and denominator. 196 over the square root of r to the 4th power. And for this one, I've got to extend my chart because 196 is the same thing as 14 times 14. So when I look at that, since 196 is 14 times 14, the square root of 196 is 14. R to the 4th is r squared times r squared. So this is r to the 2. Notice the shortcut here is just to divide that power by 2. And that takes care of number 7. Okay, we're getting into cube roots. And so these are just like square roots, but the rule is you need to find a perfect cubed. So it was 135. That's the same thing as 27 times 5. I don't know that. 27 is the same thing as 3 times 3 times 3. So 27 is what we would call a perfect cubed. So when I simplify this radical, instead of a perfect square, I'm looking for a perfect cubed. The cube of, so this is the cube root of negative 27 multiplied by the cube root of 5. And then the cube root of negative 27 is negative 3. So yeah, these are a little more difficult to deal with, but the same rules apply except for you're looking for a perfect cubed. Let's see what else we have. Okay, simplifying these square root expressions, and this is the same thing. You're going to break down each numerator and denominator separately. So we've got square root of 15 on top of square root of 100 multiplied by square root of 5. We know what the square root of 100 is. And then seems to me that I can do some division here. So I'm going to put those radicals back together and say this is the same thing as 1/10 multiplied by the square root of 15 over 5. 15 divided by 5 is 3. So this is 1/10 radical 3, which is the same thing as radical 3 over 10. Okay? Maybe it's better if we simplify inside here first. For example, 8 over 100. Can I simplify that as a fraction? Well, I can divide everything by 4. 8 divided by 4 is 2. 100 divided by 4 is 25. That looks better. So this is the same thing as the square root of 2 over the square root of 25, which is square root of 2 over 5. Looks a lot nicer. Let's take a look at this next one. This looks pretty gnarly. Put everything inside the same radical and then simplify where you can. Does 3 divide into 80? I don't think they do. But here I have an x squared and an x. That definitely simplifies. That just leaves me with an x on the numerator. And then the y cubed and the y cubed cancel out. So this is equivalent to radical 3x over 80. We can simplify the radical 80. Now we'll separate this again. And 80 is the same thing as 16 times 5. Square root of 16 is 4. And then now I have a radical in the denominator that I need to get rid of. So what I'm going to do is I'm going to multiply it by radical 5 over radical 5. So when I do that, the numerator becomes radical 15x. The denominator becomes 4 times radical 5 times radical 5. And how much is radical 5 times radical 5? Well, that's just 5. So this is equivalent to radical 15x over 4 times 5, which is radical 15x over 20. Now that was a long way, and I probably would have simplified a couple of the steps out. I probably didn't need to show this step or maybe even this step. But, as you're beginning, you do need to show all of that work. Let's talk about that conjugate for number 17. To multiply a conjugate, remember it's the same as the radical expression except for you change the sign of whatever term has a radical. So for this one, 5 over negative 3 minus 3 rad 3, I'm going to multiply this by negative 3 plus 3 rad 3. Okay. Then let's multiply that out. As you can see, the numerator, you're basically going to distribute that 5. But for the denominator, we need to do something special. And I'm going to do it over on the side of the paper. So I've written those two conjugates out, and I'm going to multiply them out by foiling. So let's FOIL. First times first. Outside times outside. Inside times inside. Last times last. Well, last times last is, I'm going to actually write this out. That's going to be minus 3 rad 3 times 3 rad 3. Okay. I'm going to simplify, write that out real quickly. And then notice what happens here. Because we chose the conjugate, these two terms, which represent the outside and the inside part of FOIL, those are going to cancel out, and they will always cancel out if you're going to use the conjugate. So I'm left with the 9, And over here, 3 times 3 is 9. Radical 3 times radical 3 is 3. And then 9 times 3 is 27. How much is 9 minus 27? Negative 16. Or maybe 18. Okay, the last thing that you need to do here is just to, distribute that numerator. So that's negative 15 plus 15 radical 3 on top of negative 18. All right, so there it is. I apologize, that's not the easiest thing, but we can notice something interesting. When we FOILed, this part right here, this was negative 3 squared, and this part right here, this was 3 rad 3 squared. So when you multiply the conjugate by the conjugate, you actually create a difference of squares. So we'll do that real quick for let's do number 18. Okay, change to green also. This is going to be 3 over 4 plus 4 rad 5 times, and then the conjugate would be 4 minus 4 rad 5. Okay. Distribute on the numerator. Hopefully you'll get quick at that, but that's 12 minus 12 root 5. And then the denominator, how much is 4 times 4? Well, that's 16. How much is 4 rad 5 times 4 rad 5? Well, that's 4 times 4 times rad 5 times rad 5. 4 times 4 is 16. Rad 5 times rad 5 is 5. 16 times 5 is 80. Okay, so that's just 16 minus 80. Okay, so we've got negative 12 minus 12 rad 5 over negative 64. And as I'm looking at this, everything here can be divided by 2. So why don't we divide everything by 2? No, everything can be divided by 4. Why don't we divide everything by 4? 12 divided by 4 is 3. 12 divided by 4 is 3. 64 divided by 4 is 16. There you have it. We're going to do one of these just to finish things up, but we're going to try to simplify the expression. So the first thing you're going to do is if you see any radicals, we can simplify them. I notice that rad 8 is the same thing as the square root of 4 times the square root of 2. That's 3 times 2 square root 2 plus 3 times square root of 2. And 3 times 2 is 6. And notice that we have like radicals. Square root of 2 is the same thing as square root of 2 here. So I can combine them kind of like they were variables. So I've got 6 rad 2's and I got 3 rad 2's. Together that means I have 9 rad 2's. So that's it for this section of the math journal. There was a lot to do here, So hopefully you can replay what you need, and I will talk to you guys later.